Thank you, Jakob. Thank you to the organizers. Good morning to the Australian ones. We're going to watch the talk tomorrow, I guess. So what I'm going to talk about today, it's very different from what we've been seeing the whole week. So I apologize for this. So there's going to be no more tests. There's going to be just a little bit of rep theory, but the motivation is very much comes very much from representation theory of quivers. So that's really why the title didn't stick into your mind. So I'm going to tell you what I'm going to talk about. So it's going to be about totally nonnegative Grassmannians. Grassmann, a lot of Grassmannians. Grassmann necklaces. And quiver Grassmannians. So that's recent joint work with Alex Puetz and Evgeny Feigin. Somehow the original motivation of, at least to me, to a couple of papers with Alex and this paper with Evgeny has something to do with understanding geometry of quiver Grassmannians. So that's, a very vague statement, especially because one can prove that every complex projective algebraic variety can be realized as a quiver Grassmannian. So that statement, understanding the geometry of these objects, it's a bit empty in some sense. It's hopeless to understand everything. So my idea was, okay, let's try to understand which class of them, so whether this realization can help us to attack some problems. So for example, to play with equivariant localization. So we saw in Mark's talk before that it's very useful if you have a torus action on a variety. And then Jens was mentioning that in some nice cases, if the torus is big, so we saw rank 1, so a C star again acting before. But if you have a bigger rank torus, which acts with a finite point, with a finite number of fixed points and one-dimensional orbit, plus your variety is nice. So for example, amidst a cellular decomposition, then you have an even more explicit version of equivariant localization, which is due to heuristic objects and McPherson, where you can describe really the cohomology ring structure in a very nice combinatorial way, which is encoded in a graph. So, and with Alex, we looked at quiver Grassmannians coming from certain representations of a equi-oriented cycle. You can, in fact, construct this very nice torus action. So that was somehow the origin of everything. And then last year, Evgeny noticed that for a particular class of representations, you would have some nice underlying combinatorial structure. So combinatorial structure in the same sense that was Yapin, who was saying in the talk we saw. So meaning she was looking for, if you want, a nice set parametrizing the basis, for example, of the cohomology as in a building group, as a module. And so he noticed that what we would get as a basis for the equivariant cohomology of a certain specific variety was, would be the same underlying combinatorics than a poset, which is known to control the some cellular decomposition of the totally nonnegative Grassmannian. So that's the whole thing. So today I'm really going to talk about this relation. So Grassmann necklaces is somehow the combinatorial part, and they are bridging these two words. Okay, so I'll start from this because somehow it's how I've got to know also Grassmann necklaces, and then we're gonna talk about the combinatorial side and finally about quiver Grassmannians. Okay, so what's this CNN Grassmannian? Well, in fact, they are like a very special case of a much wider theory of total positivity, which has a long story, which I'm not going to talk about. So there's also, let me mention this, it's a special case also of Lustig's So Lucy studied the totally non-negative part of every real partial subvariety. So that's a particular case. And we're just going to look though at a very elementary definition due to Postnikov. And so I'm not going to discuss the general case. So we start with the real Grassmannian of k-dimensional subspaces of Rn. So this can be embedded in the real projective space of dimension n choose k minus 1. And so you take one point in here, so that's again a subspace of R to the n. So we partially saw it. We said that we could somehow represent it by a k times n matrix in the previous talk. And so what you're doing here is really just taking the collection of maximal minors. So of the representing matrix. This is well defined after common scalar factor. And this is one for every cardinality k. This is my notation for the set of k subsets, the subset of k of cardinality k of the set of numbers from 1 to n. Okay, and then here one can look at what's called the totally non-negative Grassmannians, which consists of the points such that the corresponding Hooker coordinates have all the same sign. So you can find, if you want, a matrix representing this subspace whose maximal minors, so k times k minors, are all positive, all non-negative. Okay, same sign meaning also 0. So what we're going to do now is to decompose it into a union of balls. Okay, so that's the first result. So in order to do that, let me define what positroids are. Maybe I write it here. Sorry, I haven't been giving Blackboard talk for ages, so I have to recall how it goes. So let's take a point. That's my real Grassmannian of k subspaces. Then I define NB for the positroid. This M is because one can prove that it's matroid of whatever. I'm not going to talk about it. So this is a subset. So that's a set of k subsets of this set, corresponding to the Hooker coordinates, which are non-zero. And again, this is, not well defined like the specific value, but being non-zero or 0 it is. And now, so if we take the collection of all of these sets of k subsets of M, appearing in this way, this is the set of positroids, k and positroids. And these are indexed in a cellular decomposition of this guy. So B, this is just in here. So you take this NV, but where V now varies all in the totally non-negative Grassmannian. All right. And now what one can do is to look at CN whenever one thinking out of this in here. And this is just the locus of points whose positroid is exactly M. Okay. So now it's clear that we are decomposing the totally non-negative Grassmannian in CNs. Okay. And so the theorem is that they are all balls. So that's a Postnikov theorem. As let me just write this way. So the totally non-negative Grassmannian decomposes as a union of this. And this is homomorphic to R, the positive part of the real line, to the sum, some SM.
Can I ask a quick
Yeah,
question?
sure.
If you forget the totally positive condition, are they still
It's a-
walls?
No, it's a complete mess.
Really?
Indeed. Yeah. That's it's a real. So you can't. Oh well, they're still balls.
But yeah, I mean, you just forget that D has a totally positive. You just look at all the same thing. You just fix a. It's a non-negative one.
Yeah.
You look at the ones you fix those indices for which the cubic coordinates are non-zero.
I mean, it wouldn't be really cool. Right?
Be a unit.
But yeah,
But anyway,
I don't know.
never
I mean, somehow. So I think that one usually restrict to this because you get this matrix structure, and in the other case, it's very hard to control what happens. So whether they're empty or not, for example.
Yeah.
I mean, empty or not. Well, defend this way is not clear, but yeah, which ones are intersecting and how. So in this way, one way of thinking about it is that, so here what you can do is that you can take your Grassmannian, that you look at the Bruja decomposition, but then with respect to all possible worlds. So you have a lot of different cell decomposition, then you intersect all of that, and then you intersect it with the totally negative part, and then you get this.
Oh.
Well, no, not exactly this. This would be very complicated. That is Gorisky, Serganova, Gelf, and McPherson. But if you take some cyclic shift of, specific elements indexing your Borels, so those Borels are conjugated in GLN, so you pick specific permutations, you intersect these different stratifications together, and you would get that.
And is this a cell composition?
This is cell decomposition. Yeah. That's I guess what's going to come very soon. Yeah. So yeah, when one has something like this, there are let's say also that there is plus cell decomposition. So this is cell decomposition, meaning that if I close one up, I find a distant union of the others. Of other pieces are type CNs. So now, I mean, it's sort of not very satisfactory this way because this pi kn, it's coming. I mean, you can't just say which subsets you're really getting this way. So what you're going to do now is to provide a different parametrization of the cells, which has, in fact, is a set which has a poset structure, and the poset structure is the, let's say, the opposite to the one coming from the closure of cell inclusion. So whenever one has a set parameterizing a cell decomposition, you get automatically poset structure on it. Just saying that one element is less than the other if and only if the corresponding cell is contained in the closure of the other one. Now we're gonna, so these Grassmann necklaces are going to be the opposite poset to this one. And in fact, spoiler, they are going to be exactly the poset we want for a cellular decomposition of the appropriate Grassmannian. We're not at the end about it. So maybe there's like two questions that I want to address, which is what I was saying. So whether we can find somehow combinatorial, let me say combinatorial parametrization in the sense which I said. So somehow we seize also the poset structure of pi kn, And then if we can also find a nice way of determining this dimension. What about again, if you have in mind what happens for the Bruhali composition, the statement of the flat variety, the statement is very clean. You just say, well, the dimension is the length of the corresponding element of the bulb, so the function length. Okay, so here we are. So here we need to introduce now these guys. So let me just give you straight the definition, and then we'll see what they're called necklaces. So K, again, we have our K and M fixed because we want to deal with Grassmann KM. So a KM Grassmann necklace is a collection of subsets of the set of the first set numbers satisfying the following condition. So what we want to happen is that whenever I pick one of these sets, it either coincides with next one. So IA is in some relation with the following one. So they either coincide, or if I have A containing IA, I can remove it and put another element. Okay, so another way of saying this is that IA is contained in IA plus 1 union A. And here, so for example, if I put 3 and 3 equals 2, I could take as I1, 1, 2. Now 1 is contained, so 2 I have to keep it. I could, for example, put 3. Now 2 is contained, I could remove it, and I could put 1, and indeed this is also satisfied. Okay, so this has to be intended for that. So I also have, meaning that I also have that IN is containing I1 union N. Okay. And so here you see that I do have my I1, and then I have my I2, and then I have my I3. Okay. So you can think of it really like a necklace where either, well, 2 rings coincide, or they just encounter in like one piece. All right. So now, as I said, so the theorem is going to be that they are, so if I look at the set of K and Grassmann necklaces, they are going to parameterize my cells. And then I want you to say something about the poset structure. So let's introduce a partial order on this set. So maybe I'll do it here. So the partial order goes into, so I need like 3 steps. So first of all, I want to consider a total order on M. And this is just, so here I have an A. For any A, I shift the order cyclically, the order of the numbers. So this is a unique total order on N, such that A is less than A plus 1, is less than 1, less than 2, less than A minus 1. And here I put an A here just so that we don't get confused. Okay. If I have an order on this set of numbers, this of course induces a partial order on the set of K subsets of N. Instead of having the usual one, you just shift it. So meaning, again, if you take 2 K subsets, you reorder them according to the total order, and then you just compare these 2 entries. And so at this point, we get an order on.
You mean lexicograph?
With respect to this.
Yeah.
Yeah.
What's the usual one? As in forgetting the A.
Oh no, the usual one I would say 1 is less than 2 is less than 3.
No, that's what I mean,
yeah.
but on K subsets, how do you tell us the usual one?
Yeah, it's not for the Grassmannian. So if you have 2 K subsets of numbers from 1 to N,
yeah.
Well, each of them you can completely order it,
yeah.
right? So in increasing way. And then you just compare.
I see, the first one is the
Pairwise,
same, and then
yeah.
the first one which is bigger.
Yeah.
Okay, thank you.
No, yeah, I mean, not the first one, which is bigger.
The last one which is bigger.
No,
Which-
like pairs. So otherwise they're not comparable. So like,
Oh, I see,
yeah.
I see.
it's like for the
It's a
Grassmann.
partial order.
It's a partial order.
I see.
Yeah. Yeah, because, yeah, it's a
Gotcha.
poset. Yeah. And so now this is here I wrote it, partial order. Yeah, and here we also get the partial order on DKN, just saying that this now is a collection of k subsets. And when I take the ith ones between two, so let me just say I is less or equal to I prime, this is going to be the collection of IAs, this is the collection of I prime A's. Then if and only if, again, I A is less or equal A, I prime A, for any A. Okay. So for example, maybe let me make an example here. Yeah, so for example, this element we have here is the minimal one in the poset group 2, 3. Because this is the minimal with respect to the 1 order. This is the minimal 2 subsets with respect to the 2 order. And this again, the minimal 1 with respect to the 3 order. And now the theorem by Postnikov is the following, is that there is a bijection, which I could write down, but I will not, which goes from positoids to Grassmann necklaces. Just write I dot M, which has the property that Cm is contained in the closure of Cm prime. Infinitely, if the corresponding Grassmann necklaces are in the opposite relation. Okay, so now we have, so that's sentence pretty, because you have nice combinatorial structure to tell you how these cells are glued to each other, so what you find on the border of one cell. But now we had another question, which was about the dimension. And I'm going to jump to another combinatorial guy. But I want to keep this. Let's write it to big. Let's try to write it here. So the other combinatorial structure I want are affine bounded permutations. So again, Feigin of affine bounded. It's a bijection from Z to Z. So such that, first of all, this is uniquely determined by the values of the first entries. Then you have some condition on how much. Q plus n.
Oh, okay.
Yeah, sorry. Yeah, I wanted someone to be static. So that's the thing. So you really do care about what happens in the first 10 entries. And somehow you have some conditions about the sum of all of how much this function is increasing. So it's different from the point you apply to it. And then it cannot jump too much, in the sense that fi minus I goes between 0 and n.
Saving two, just sum.
Yeah, sorry. Okay, thanks. Yeah. Right. So now let me give an example, maybe since I messed it up. At least you see an example, so let me write down the boring one. So for example, the function which says I to I plus k satisfies all of these conditions. So this is somehow maybe the only ones. Okay, so always let's say we always assume k to be less than m, because otherwise we always have in mind that k is the k-dimensional subspace is on some n-dimensional space, and then this condition is at this point just satisfied, and this is also satisfied. So what I was saying is that I would like to play a similar game as what one plays when one has, yeah, for example, defined boundary. And so here the length of f, here is nothing but again the number of inversions. But again, we have to remember that somehow we really just care about the first n entries. So what we are taking as the pairs of I varying in the first n numbers. Here we just take all numbers from 1 to m or whatever. So here's I less than j and fi greater than f. So what I was noticing is that if you look at this example, this is just an increasing function, right? And so this has to have length 0. So that's why I'm that cool. That so I think you can probably embed it, but it's not usually. I mean, usually the usual way you would have bijection from Z to Z satisfying certain conditions, and then again the length is exactly defined this way. So we are using some. Okay, so that's the length. Now the theorem. Lamb in this formulation is that so there is, let me be again big, there is a bijection from Grassmannian X to, let me write it, B an is our an bounded find combinations which take I to some fi. And this again, this is easy to write down. Maybe yeah, I'll speak it. It's it is like you just say that it sends A to A if A is not contained in IA, and then it uses the fact that IA plus 1 is going to be IA minus A plus another element to determine the image of the element. So anyway, there is a bijection, and this is such that if we take like this for any positroid, Feigin positroid, it holds that C is isomorphic to R greater than 0 to the K n minus K minus the length of the corresponding bounded permutation. So we're saying that, so if you want, you can just say that we have a positroid, then you can translate it to Grassmann necklaces, then you get the corresponding permutations, and then this way you can determine the codimension of this. Anyhow, so as I said, what I want to talk about is a very special Grassmannian, or a linear algebraic analog of this combinatorial pattern. So, I'm not gonna give a lecture about quiver Grassmannians because it would take very long. But just let me say that what we're because we care about one specific representation. So let me just say that what we're interested in is this quiver. So as I said before, so it's the A-oriented with n vertices. And here we move to complex algebraic geometry. So here what we are going to deal with is a specific representation of this guy, meaning it is a configuration of complex vector spaces and of maps. So what I'm going to look at is a representation in which where the vector spaces are all CNs over any vertex. And the map is going to depend on the specific error. So what we do here is really we work with coordinates. So we fix a basis of CN. So we define a projection operator for any A from 1 to n, which fills the A's vector. I goes to I, if I is different from A, and otherwise is 0. And this is the corresponding map. So I say I go from the first copy of CN to the second one by killing the first vector and doing nothing to the others. And here I kill the second one, and here I kill the eighth one. The eighth one. So now what one can do in general is work with the category of representations of quivers and now look at some objects of a prescribed dimension. Okay, that's a quiver Grassmannian. So, but I'll just give you the explicit definition. It's called XKN. And this is given by collections of vector spaces. So these are really, if you want, points of the complex Grassmannian, KN. Yes, so here really means K subspace of the specific copy of CN, which are preserved by the morphism. So now this is clearly embedded in the product of Grassmannians, and this condition is closed. So in particular, it's a complex projected algebraic variety, which is, and it is in this case, singular in general. And it's, so at least for me, so before starting working with quiver Grassmannian, I was used to work mainly with subvarieties, and which are normal, they're super nice, and these are not in general. Okay, so that it's way more complicated in principle to deal with that. All right, so let's look at this guy. Let's take a point, for example, in there, just to make sure that it's not empty. So let's look at an example, K1 and 3. Okay, so I have to pick 3 lines inside C3. So N1, N2, and 3. So I start with N1. I could pick the line through generated span by the first basis vector. Then if I apply the first projection, it dies. So here I can pick whatever I want. So for example, the line spanned by the second vector. Now 2 dies again, and I can take the line, for example, generated by the third vector, and now it dies. So this is a point, okay, in my x1 3. Well, in fact, I guess now you can see that whenever I pick a Grassmann X and I look at the corresponding the spans or the corresponding basis vectors, I get a point in there. Okay, so let me write it here. Or maybe I can write it here. And then, so the observation is that in general, whenever I take an I, then there is a corresponding point in XKN where this is given by and say AI is the span of EJ where J is in IA. Okay, this is exactly. So instead of being a discrete set, now we got a variety. Okay. So the theorem, as I said, joined with Evgeny and Alex, is the following. So X Kn is the disjoint union of I, where I is a Grassmann necklace. And this can be explicitly constructed either themselves as quiver Grassmannians or as out orbit. Well, not really as quiver Grassmannian, sorry. So we can construct them as, so you can, that's a notion of automorphisms of quiver representation, so that's what I can look at. So of my representations with all CNs. Applied to the corresponding points. And then, well, this is exactly the same. This is in fact isomorphic, so that's an affine space. So this is nothing but a complex affine space of the length of the corresponding bounded affine permutations. Well, then the other question was, what's the poset structure? And so we're going to have the cells corresponding to two different Grassmann necklaces are in this relation, if and only if I is less or equal to 1 prime. Okay, I think so. So then maybe I'm just gonna cut. So that's the first part of what we have. So now what one can do, which is what I really like, as I said, is to prove that there exists, or maybe I write just one sentence. So there exists an algebraic torus acting on this quiver Grassmannian. So there is one torus that it's obvious that it acts, which is just the one which rescales all INs. And it is also clear that with respect to that torus, the points we define are fixed points because they're coordinate subspaces. But this is bigger. That torus wouldn't be good for this Goretzky-Patterson theory because it would get infinitely many one-dimensional orbits. So you do nothing to get a combinatorial description of the homology. But this is a good one. Okay, so there exists an algebraic torus acting on this variety such that the cellular decomposition is stable. So for any I, the cell is preserved. And then what I was saying, so the T-fixed points are exactly these points. And then let me just say one-dimensional orbits are finite in finite number, and they can be combinatorially described in terms of pairs of Grassmann necklaces. So this is somehow, one should see it as a, so when one look again at the flag variety case, one knows that there is a one-dimensional orbit, for example, in the case of GLM from fixed flags, if and only if the two permutations are related by a transposition, and you get a very close condition here. So it's an analog. So you are sort of transposing an interval in a Grassmann necklace. So that's a cyclic interval, so you are exchanging two elements, but all in the same Grassmann necklace. And so this allows one to describe combinatorially the equivalent homology ring of this by applying Goretzky-Patterson theory. And not only that, so these cells, so this group is solvable. So in particular, you get a weakness stratification, so you can also look at equivalent intersection homology. So once again, you have a combinatorial description of the monograph, so you can apply Broader-McPherson techniques to compute it. Okay, that's all. Thank you.